Hi guys, and welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on beam with a traveling load. And this example is from structural physics or structural mechanics, which is not my specialty as a chemical engineer in training and education, some electrical engineering in practice, but I really haven't done much with structural mechanics, so I'm pretty much just going to follow this example. Alright, so we're going to be learning together today since it's not my expertise, and let's get started. It is a little bit of a longer one. This is like 16 pages long, so hopefully it doesn't take an hour, but let's get going. So the background information is, in some problems, the load changes position with time. It can be a train moving over a bridge or a heat source moving along a weld. In this example, intended to show how to model traveling loads, a set of load pulses travel with a beam with equally spaced supports. The model is parameterized, so it's easy to change, for example, the velocity of the load pulses or the spacing between them. This is used for showing that for some load configurations, resonant vibrations will appear in the beam. So on modeling the traveling loads, the possibility to enter analytical expressions and use built-in or external functions in the input fields for loads and boundary conditions makes it easy to model traveling loads in COMSOL. And again, we're using multi-physics only, no additional modules. A load with a constant distribution moving with a constant velocity v can mathematically be written as f, a function of argument x minus vt, where x is a vector and v is the velocity vector. This is the type of load being used in this example. You can, however, use completely arbitrary functions of space and time. When the load is moving during the analysis, it will in general only cover some elements partially. This is not a problem since the load is numerically integrated. The element size should, however, be chosen such that several elements are covered by the load. On the geometry, they give us the geometric parameters we'll be using. Number of spans is 8, length of individual spans. Okay, so each span width is 10 meters. So if there's 8 spans, that means the total covered is 80 meters. The beam height is 0.3 meters. And for the material properties and boundary conditions, we're given the material is concrete. And this is a material in the built-in library that we can just look up. So the Young's modulus will be 25 gigapascals. Poisson's ratio is going to be 0.33. Mass density, rho, is 2,300 kilograms per meter cubed. The beam is supported on one point at the end of each span. The load travels along the top. The loading is controlled by the parameters listed in Table 2. So I'm assuming we will input these, or actually I think I already, it was a table I downloaded in a text file, so we'll just upload those. So load speed, we have 4 different values to look at. Pulse spacing, we have 1 pulse only, a pulse of 2 times the span width, and a pulse of 1 span width. Oh, 1 pulse every span width. Okay, the pulse width and the load intensity. So we're going to be analyzing 4 different combinations of loads in the modeling. 1, a single load pulse traveling with a speed which is slow compared to the natural frequency of the beam. 2, a single load's pulse traveling with a speed which matches the natural frequency of the beam. So in both of those, we're just following 1 pulse. 3 and 4 are going to be intermittent pulses. So 3 is a pulse train traveling with a speed which matches the natural frequency of the beam. the distance between the individual load pulses is 2 span widths. For a pulse train traveling with a speed which matches the natural frequency of the beam, and the distance between the individual load pulses is 1. And then for the results, the lowest eigenfrequency of the beam can be computed analytically and is independent of the number of spans. It's actually the same as for a simply supported beam with the length of a single span. So we can compute the eigenfrequency by F0 equals pi over 2 times the square root of EI. E looks like it's Young's modulus here. I, what is I? Inertia? It doesn't define I. I don't know what I is here. Is that moment or something like that? Well, I guess we'll figure it out. Over rho, the density times the area, I'm guessing A is the area, times LS, which is the span length, to the power of 4. So it's evaluated to be 4.49 hertz for a concrete beam. It can thus be expected that a load travels 1 span, LS, during half the period T0 of the lowest natural frequency F0 should be able to excite a resonant vibration. This critical velocity is then approximately VC, critical velocity equals LS, the span length, over half of T0, which is, what is T0? I guess the, it's not defined, but I guess T0 is the critical time, residence time, or something like that. Where was I? Okay, equals 2 times length times F0, the lowest natural frequency, which comes out to 89.7 meters per second. So that is our critical velocity. The effect of changing the velocity of the load and the spacing between the loads is shown in figure 1 down here. So we've got the first scenario, kind of bumpy until it levels out here, and then it's flat. Green is the load speed. The scenario 2, 3, and 4 have the load speed of 86.699 meters per second with different pulse spacing. So we've got scenario 2 is the green, scenario 3 is the red, and scenario 4 is the light blue. Displacement history at the midpoint of the first span as function of the location of the first load pulse. Alright, so at a low speed, 20 meters per second, the solution resembles a stationary solution. Alright, well, we'll get into that as we build it. So let's go ahead and start with the model wizard. So we're going to do a 2D model and go to structural mechanics and choose solid mechanics, solid. Add, and then we're going to do a time-dependent study from this physics. You can choose from eigenfrequency, frequency domain, stationary, or time-dependent. Because we're not interested in doing a parameter sweep for the frequency, we solved analytically already for the resonant frequency. We're really only interested in a time study, time-dependent study. So looking at from time equals 0 through some time, how does this pulse look traveling through given a resonant frequency of the material? Let's see, eigenfrequency would be used to compute eigenmodes of a linear or linearized model. Frequency domain study is used to compute the response of a linear or linearized model subjected to harmonic excitation for one or several frequencies. So you would use those in different scenarios. If you wanted to neglect the startup period here, I guess you could do a stationary, but we're going to do a time-dependent study. Global definitions, parameters 1. In the settings, locate parameters. We're going to import or load from file. And here's the text file I've already downloaded from the website. So here they all are imported. Span width, number of spans, total length, beam height, load intensity, pulse width, pulse space, load speed, T-step 1, T-step 2, T-step. And if you want to go in and open the file from COMSOL's website, you can see what each of these is. T end, element per span, F naught, the lowest resonant frequency or estimate of first natural frequency, and critical span. All right, and now we're going to move on to geometry. So let's build a rectangle. So in the size and shape, for width, we're going to enter span width, and height, we'll enter beam height. To call the parameter we defined in global definitions, and point. So to add a point, we'll go to geometry and click the point icon, and for the y coordinate, it's going to be beam height over 2. Right click point 1 and choose duplicate. So we're going to make it 0.2, and in the X text field put beam or span width, and build all objects. So there's our 2 points. We've got one in the middle of this side and one in the middle of that side. Union 1. In the geometry toolbar, click booleans and partitions and choose union. Click in the graphics window and control all, so we're just selecting everything we've built so far, and build selected. Oh, well, I clicked build all. I should have clicked build selected. Anyway, now we're going to build an array. So in the geometry toolbar, click transforms and select array, and then select the object union 1 only. In the settings window for array, locate the size, and in the X size field, type num spans. Another variable we already defined. And in the displacement for X, it's going to have an X displacement of length, span width, build all objects. Okay, and I'm going to hit zoom extents. So you can see it just built an array of the first geometry on each edge of the rectangle. Box. So now we're going to do some definitions for the points on the center line of the box. In the definitions toolbar, click box. Definitions, box. In the settings window for box, type box points on center line in the label text box. Locate the geometric entity level section. In the level list, choose point. Okay, and it automatically detects all the points here along the center line. Locate the box limit section. In the Y minimum text field, type beam height over 3. And then the Y maximum text field, type 2 times beam height over 3. Locate the output entity section. From the include entity if list, choose entity inside box. Include entity if the entity is inside the box. So that would be all the points along the center line. Box boundaries above. In the definitions toolbar, click box. So again, we're going to create a unique label for this one, boundaries above. And for the geometric entity level, now we're going to choose boundaries. And for Y minimum, we're going to put 2 times beam height over 2 and nothing for Y maximum. Right, so that's just the top of the beam basically. And locate the output entity section from the include entity if list, choose entity inside box. Add material. In the home toolbar, click add material. And from the built-in or add material window, we're going to search for concrete. Okay, so it looks like there's multiple listings for concrete. I'm not sure these are different. Oh, so we want the built-in concrete. So I'm just gonna double click on this and it'll add it to materials. I can close the materials toolbar. And now we're ready to define the physics. So we're gonna go to solid mechanics and click on linear elastic material 1, damping 1. In the physics toolbar, click attributes and choose damping. So up here in the physics tab, I'm going to go to attributes and click on damping, and it appears under linear elastic material 1 in the model builder window. Alright, so we're going to set the damping parameter BDK stiffness damping parameter to 0.002 seconds. And now we're going to add a fixed constraint. In the physics toolbar, click points and choose fixed constraint. In the settings window for fixed constraint, locate point selection. And we're going to change this to box points on center line. So it selects all of our center points here. Definitions. Create functions describing the load. The distribution is rectangular load. So for rectangle 1, in the home toolbar, click FX functions. So it's this FX icon, and we're going to choose global rectangle. And the settings window for rectangle, locate the parameters. And for the lower limit, we're going to make this 0.5 times pulse width. And the upper limit is going to be 0.5 times pulse width. Click to expand the smoothing section down here, and we're going to type in the size of transition zone text field, type 0.1 times pulse width. In order to make the load pulse periodic, call it through an analytical function, which has the option of being periodic. Analytic 1. In the home toolbar, click functions. So we're already there. Click functions again, and choose global analytic. Locate the definition section in the expression text field, type rectangle 1x. Rectangle 1 is an argument of x. And locate the units section and enter argument x and units of m. In the function text field, type 1. Click to expand right-click to expand the periodic extension section. Select the Make Periodic checkbox. In the upper limit text field, type pulse spacing. And now we're going to variables. In the Model Builder window, right-click Definitions and choose Variables. Create a variable for filtering the load so that it's periodic only behind the first pulse. In the settings window for variables, locate variable section, and then we're going to enter these variables as it has shown here. First load X is going to be expression load speed times T plus pulse width over 2 in meters position of the first load pulse. Second parameter is going to be behind first load, given by X less than first load X. Description, true if behind current position of the first load pulse. Add the load definition to the whole upper boundary. The function call will make the load non-zero only at certain traveling points. Alright, so we're going to go to solid mechanics and add boundary load 1. In the physics toolbar, click boundaries and choose boundary load. And in the settings for boundary load, locate boundary selection. And from selection, we're going to choose box boundaries above, so the upper line on the beam. Locate the fourth section and specify the FA vector is going to be a 0 for the X component, and for the Y component it's going to be an if argument with arguments behind first load, the variable we just defined, comma, negative load intensity times pulse, argument of X minus load speed times T, comma, 0. Okay, and now we're going to make the mesh. In the mesh toolbar, click mapped, which is this sort of flag-like mesh icon. And right-click mapped 1 and choose distribution. Select boundaries 1 and 3 only. So I'm just going to do select all and then remove the other ones. So we're left with 1 and 3. In the settings window for distribution, locate distribution section, and for number of elements, we're going to change from 5 to 1. Distribution 2. In the Model Builder window, right-click mapped 1 and choose distribution. And in the settings window, locate boundary selection. Now we're going to change this to boundaries above once again. Boundaries above. Okay, and locate the distribution section. Number of elements text field, type elements per span, or LM per span, the variable, and build all. 2 elements across the entire way. In the study toolbar, click parametric sweep. So going down to study 1, parametric sweep is this icon here. Locate the study settings section. So we're going to click add 2 times, and in the table enter the following settings. Load speed. Here it is, load speed, and for the second one, it's going to be pulse spacing, distance between load pulses. And then our parameter value list is going to be 20 meters per second, space, critical speed, space, critical speed, space, critical speed. Oh, that is a variable, so it needs to be all together. Alright, and then for pulse spacing, our parameter value list is going to be tote length times 2 space tote length times 2 space span width times 2 space span width. Alright, moving on to the time dependent study. In the model builder window, click step 1, time dependent, and in the settings window for time dependent, locate study settings section. And the output times text field type range. So we're going to overwrite this range. 0, span width divided by load speed divided by 20, 10. So this is starting at 0, going to this, whatever that value comes out to, in increments of t end. Okay, from the tolerance list, choose user controlled. And for relative tolerance, we're going to change this to 0.0001. Solution 1. In the study toolbar, click Show Default Solver, which is this icon with the 4 flags next to each other. And in the model builder window, expand the Solution 1 node, then click Time Dependent Solver 1. So we're expanding the Sol 1 node that just appeared here. And from that drop down menu, I'm going to select Time Dependent Solver, click to expand the time stepping section. I'm going to expand this one, and then from the maximum step constraint list, choose constant. So we're changing this from automatic to constant, and instead of 0.1, enter t step, the variable we defined. Okay, and with set a reasonable scale for the displacement so that the convergence checks in the solver will be appropriate. In the model builder window, expand the study 1 solver configuration, solution 1 dependent variables. So now I'm expanding this drop down, dependent variables 1, and then select displacement field comp1.u. In the settings window for field, locate the scaling section. And in the scale field, we're going to change this to just 1e to -2. Where I went wrong is I forgot to change the function name for analytic 1 to pulse, so it didn't recognize it when I went to compute it. So let's compute it again, and now it knows to call that function now that I've named it correctly.